Chapter 6, Lesson 7, which is Applications of Sinusoidal Functions. So what I'd like to do to begin this lesson is show you a few images and have you predict what these pictures represent. So let's have a look. If you said this graph is showing the hours of daylight at different times during the year, you would be correct. And as you look at the graph, you can see that it follows a sinusoidal shape. This image is also showing daylight, but it's also showing nighttime. So this is a snapshot in time showing what parts of the Earth have day and what parts of the Earth have night. And if you look at some of the shadings on the edge, you can see which are at dawn and which are at dusk. This graph is showing tides. And if you look closely, you'll notice that this sinusoidal wave is a little bit different because we have some minimum values that are different. And we also have some maximum values that are not exactly the same as well. But by combining trigonometric functions together, we could create a graph that looks like this, as this illustrates high tide at different times of the day, depending on if the moon is directly overhead or if it's on the opposite side of the Earth. This looks a little bit like an experiment from a high school science classroom, where you look at the height of this mass that's hung on a spring. As it bounces up and down over time, it follows this sinusoidal pattern. Now, why don't you pull out your workbook and have a look at the Get Started question from section 6.7. And once you finish this question, you can restart the video and have a look at the answers. You probably recognize this initial height of 5 meters as the point where this graph starts, and that would be the height of the person when they get on the Ferris wheel. The radius of the Ferris wheel is the same as the amplitude of the function. So we did the maximum minus minimum divided by 2, because from bottom to top, that would be the diameter. Radius is half of the diameter. Now you may have eyeballed it and discovered that, oh, this looks like our center line is here at a height of 25 meters, and then just look to see, oh, from there we're going up 20 meters to the maximum, down 20 meters to the minimum. That would be another way to figure out the radius for this Ferris wheel. And here you can see we have one complete period or rotation highlighted in yellow, which gives us a time of 2 minutes for one revolution of the wheel. Now why don't you take a look also in your work text at the Construct Your Understanding question. Hopefully these are the values you came up with for the characteristics of this function. And we're asked to sketch the graph from 0 to 4. So I can choose a scale here, and we'll say 0 is here, and I'll make every 2 grid lines 1. So I can fit it on. And then as we look vertically, I can see its vertical displacement is up 2, and then the amplitude is 3, so I need to go as high as 5. So I'm going to have every 1 grid line represent 1. So I've added the scale, and I've also put in some dotted lines to show where the center line, or median, or equilibrium is. And then I've shown where the maximum and minimums are as well. It's a sine graph. It's been translated 1 unit to the right, and so my starting point will be here on the center line 1 unit to the right. The period is 2, so if I go 2 units from there up to 3, I'll have 1 complete period. And then halfway in between those 2 points on the center line, I'll also be on the center line again. The sine graph starts on the center line and curves up. So here, where my x value is 1.5, I'll be at a maximum. Here at 2.5, I'll be at a minimum. And then I'll just keep that pattern going to sketch the graph between 0 and 4. And here's what our final graph will look like. Now, a key thing that I want you to notice here is the period that we had this time. So this period isn't a multiple of pi, which makes it something that is more useful or more applicable to a different real-life situation. So by having pi in our b value, we were able to get a period that would be any number that we wanted to, and in this case it was a 2. And this also raises an important point, that for application questions, we will always, always, always be working in radians, not in degrees. Okay, so let's continue on with this lesson. Here we have an example where a piston is moving vertically in a cylinder. Now, if you don't know what a piston is, it's a part of an engine, a combustion engine, and you could search it up on YouTube and find kind of a 5 or less minute illustration of what the piston does in the engine. But it's going to move up and down in the cylinder, a little bit like that weight on the spring that we saw in that earlier example. It's starting from a minimum height, is what we're told. Every 20 seconds, the piston repeats its cycle from a minimum height of 15 centimeters to a maximum of 35 centimeters, and then back to a height of 15 centimeters. In question 1, we're asked to sketch a graph. Now, even if you have an application where you're not asked to sketch a graph, often sketching a graph will make it easier to come up with an equation to make use of for answering whatever other questions are referred to. So here's what we know. Our graph starts at a minimum height of 15 centimeters and then reaches a maximum height of 35 centimeters. And so halfway in between, we could do our calculation to find our center line. So here you can see my calculation, and I'm getting a center line, or D value, at 25 centimeters. Now, we also know that the cylinder starts at a minimum height. And so our graph will be starting here to minimum. And so if I just keep this pattern going, I want 2 complete cycles. So I'm just going to say, well, there, I'll have 1 complete cycle. There, I'll have another complete cycle. And then I'll use those points to set a scale on my x-axis. So I'm told that every 20 seconds, the piston repeats its cycle. So there's 0, there's 20, and there we have 40 seconds. So as you can see, it's not going to be super precise because we weren't given a grid, but it'll be a reasonably good approximation. So there we have our minimum values. Halfway between each of those minimums, we should be at maximum values. So at 10 seconds and at 30 seconds. Halfway in between each of those minimum and maximum values will be at the center line. Again, here I'm just approximating by eye, and then I can sketch my graph. That's not the prettiest graph in the world, but it will do. Now, as we look down to question number 2, we're asked to determine a sinusoidal function that models the piston height. And so we need to figure out those parameters A, B, C, and D. We've already figured out the D value. So let's look at some other values, we have found that this much would be our amplitude. So from 25 to 35, that would be 10. So it would give me an A value of 10. And again, if you didn't want to do it from the graph, we could use that calculation of maximum minus the minimum divided by 2, but we will get an A value of 10. And then let's look at the B value. Remember, our B is going to be 2 pi over the period. And again, that was a rearrangement of the formula that we were given earlier, where the period is 2 pi over b. In this case, we know that our period is 20 seconds. So 2 pi over 20 is our b value. We could leave it like that, and sometimes it is, just out of convention. Sometimes it is simplified. So let's go with the simplified version, and we'll get pi over 10 as our b value. So there's D, there's A, and here's B. And again, we're at this point where we need to decide, do we want this to be a sine function or a cosine function? So let's look at a few possibilities. One option will be to say, oh, this could be the starting point of a sine function. And that would be halfway between 0 and 10, so that would be at 5. So for a sine function, I could go with my c value equaling 5 units. So let's write what that equation would look like. So we'd have our height as a function of time. And here, make sure you're careful with the variables. Since we have h defined as height and t as time, don't use x's and y's unless you redefine y to be the height, x to be the time. So our a value was a 10. Pi by 10 was the b value. And then the time minus our c value plus 25. So this is one equation that would work. Suppose we wanted to do a cosine function instead. Well, for a cosine function, remember a cosine function starts at a maximum. So I could look at this point up there. Maybe I should use a different color to make it stand out more. Use the purple. There we go. So that would be the start for cosine. So I could, over here at the side, say for a cosine graph, my c value could equal 10. So we could write out an equation for that, but I'm not going to bother. Instead, what I want to do is say, well, what if we looked at a cosine function where we're starting at 0? So cosine starts at a maximum, but if our graph starts at a minimum, we could think of this as being a reflection in the x-axis. In other words, if I made that highlighted point my starting point for a cosine function, then I would say that there's no phase shift, but the reflection will make my a value negative. So another option for an equation here would be h of t would equal negative 10 cosine of pi by 10 times t plus 25. Now, if you enter both of these on your calculator, then you should see that the graphs are identical. Again, make sure your graph is in radian mode, because if it's in degree mode, these graphs will not look identical. So applications, always in radian mode. Once you have that function graphed, what would you do to answer question 3? Well, we want to find what is h of 26. So if we're looking at the graph, what we can do is we can look at the point where we have 26 as our x value, and then we'll see, well, where does that intersect with the graph here? So if you trace on your calculator, and then you just type 26, enter, it will give you that value. And the value you should end up with is 28 centimeters is what we get. Now, if we didn't want to use the graph, what we could do instead is just substitute 26 into either of the equations and evaluate to figure out what the y coordinate would be. And again, we'd get the answer of 28 centimeters to the nearest centimeter. Let's look at one more question here. And why don't you take a few minutes to see what you come up with. Again, as I suggested in the previous question, even if we're not asked to sketch a graph, sketching a graph is helpful. So that's what I'll do, even though we're not asked for it. If you want to skip sketching the graph, you're welcome to. But pause the video here and see what you come up with for an equation. So here's what I've got. I had a maximum height of 165 meters and a diameter of 150 meters. So that enabled me to figure out the minimum height as well. And if I know that the diameter is 150 meters, I know that my radius will be my A value. That's going to be half that. So that'll be 75 meters for my A value and my radius. For my D value, I can, this time let's go from the minimum, which is 15, and I'm going to add the amplitude of 75, and that'll give me 90 for my D value. As an alternative, or just as a check, I could have said from 165, I can subtract that radius of 75, and again, I would get 90 as my D value. I know my graph starts at a minimum once again, and the period is 32 minutes, so it'll end at a minimum. Halfway in between at 16 minutes, I'll be at a maximum. Halfway between 0 and 16, I'll be on the center line. And between 16 and 24, I'll be on the center line again there. So here you can see one period for my graph. We weren't asked to sketch it. You could have sketched two or more, it doesn't matter. Well, knowing the period, we can calculate our B value. So again, in radians, I'll do 2 pi over that period of 32. This time I'm just going to leave it like this and use this as my B value. And again, I can decide what I want to do for a C value. The equation that we didn't do last time was a cosine function without a reflection. So let me do a cosine function without a reflection this time. So if I do a cosine function, cosine starts at a maximum. So I could look at that point and say that this will be my C value of 16. And that gives me all the parameters that I need in order to write this equation. And here we have one possible equation for this situation. Here are a couple other equations. So we always end up with lots of possibilities for equations we could come up with. And in fact, I could have imagined that the phase shift was to the left instead of the right. And so in the green equation that we have here, I could have done a plus 16 because I would have had a maximum at a time of negative 16 seconds as well. Now, whether that time is meaningful in this situation or not doesn't really matter because it creates the sinusoidal shape that we need for this function. Okay, and then you can go ahead to question 5 as well. And we want to estimate the height of the capsule 20 minutes after the wheel begins to rotate. And then look at question 6 as well. When did the capsule first reach a height of 120 meters? So for question 5, at a time of 20 minutes, I'm getting 143 meters for my height. Now I showed it plugging it into the equation just because I can't easily show you a graph here, but it would be perfectly fine for you to do this from the graph on your calculator. Again, I would trace and then type in 143, enter, and there you go. Now for question number 6, if we were going to do it graphically, what we would want to do is graph a second function as well, which would be y2 is equal to 120. And so what that would look like on our graph is that, well, let's see here, this is at 90. So 120 is up here somewhere, and we're looking for this value. So we graph this y equals 120, and then find this intersection point, which we expect is going to be here, somewhere a little bit bigger than 8. And as I find that intersection point, I'm getting a value that's approximately 10 seconds. So we'd find the intersection point and say that is going to be 10. Oh, it's not in seconds, it's in minutes. So careful with the units here. So that'll be in 10 minutes time. Now consider the next question. In one rotation of the Ferris wheel, how much time does a rider spend above a height of 120 meters? Give your answer to the nearest tenth of a minute. Well, if you look at the graph on your calculator, I'll look at the one we sketched up here. What we want is we want to find this next time that we're going to reach that height and find out how much time are we in between here, how much time passes. So if we find this value here, this previous amount that we had here, let me just clean this up. And here we can get a value of about 21.9 minutes. And so if we want to know the time in between those two, then we can just subtract them. So we'll do 21.9 minutes minus 10.1, which will give us 11.8 minutes as the amount of time a rider will spend above a height of 120 meters during one rotation of the Ferris wheel. All right, here you have some questions that you can practice from your work text. And that's the end of Chapter 6.